On Tuesday, Jim Riding described how there are these massive late Paleozoic reefs to the southwestern United States that demonstrate that even in spite of the so-called bioplankton blackout, nevertheless, you had really diverse and abundant ecosystems and presumably productive at that time as well. So in my talk, I will describe, I should start. In my talk, I will describe an assemblage of Polyplacophoras, chitons, from one of these very massive reef deposits right here, the Capitan Reef from West Texas. And the chitons that are in my eye were preserved at the very foot of this massive reef in debris flows, and they were very rapidly buried, obviously, and very rapidly silicified. And this was fortuitous because it preserved these otherwise fragile chitin valves in great abundance as well as diversity. And so probably the most interesting aspect of these chitons themselves is that this is really the most abundant, diverse, and well-preserved chitin assemblage known from the late Paleozoic. And so in that way, it really provides a nice window into the nature of late Paleozoic Polyplacophora at a time when chitons were beginning to look a little bit more modern compared to the earlier Paleozoic forms. So you can see a little bit of the morphological disparity here in overall valve outline, in the jugal angle, in anterior view projections of the underlying layer. All these sorts of things are variable within these chitons here. And in order to understand, obviously the most important aspect, in my opinion, of this work is the taxonomic description of these fossils. But if I were to have submitted an abstract for that, it would have been rejected for a talk, and it would have bored you guys to death. So I will try to emphasize the overall significance of this assemblage and not go into the details. But in order to understand the significance here, we need to remind ourselves a little bit of the morphology of the chitin shell plates or valves. That's what I'll refer to them as. Here, shell plates is probably a better term, as Leslie Turns has pointed out before. And probably the most important thing to point out about these shell plates is that they consist of fundamentally two distinct layers. You've got an overlying layer, and this is the part that's visible on the dorsal surface when you look at chitin in the field. So that's the tegmentum. So that's this spongy, relatively soft layer, even though it is calcium carbonate, it's aragonite. Below that, you've got the articulamentum layer here. So here's the tegmentum, and there's the articulamentum below it. Here's the articulamentum layer down here, the tegmentum above it. All this here is tegmentum. The articulamentum layer, as you might infer, it articulates. So it projects anteriorly as the sutural laminae that you can see there that insert underneath each preceding valve. In addition to that, they also extend laterally as insertion plates that stick the chitin into the girdle. So those are the two main features of chitin valves, the two main layers of the shell. And one of the things that these Bell Canyon chitons, that's a formation that these guys are preserved in, one of the things that these show is these are some of the earliest examples, barring one species, the earliest examples where you get a relative reduction of the tegmentum relative to the articulamentum layer. So the sutural laminae get relatively much larger compared to the part that would have been exposed in life. So you see this here for the first time in three distinct lineages. You also see it a little bit earlier than this in a very strange carboniferous chitin, glyptochitin, and you also see it in some more recent forms as well. So here's amicula, and then cryptochitin, it has lost its tegmentum in entirety. This is the famous gum chitin, the largest chitin in the world. So it completely lost its tegmentum. So this is clearly convergent because of the fact that where you see these cases of the relative reduction of the tegmentum, these species are not closely related at all. So you see the first example of this reduction of the tegmentum. It's clearly convergent. In addition to this, you also have details not only of the relative proportions of the tegmentum and articulamentum, but also the fine structure of these. So they're really nicely preserved. So what you can see here, not only in terms of the sculpture on the tegmentum surface, but you can also see the openings of the so-called SE canals. So the SE canals infiltrate primarily the tegmentum layer. They also, in modern chitin valves, go to the articulamentum in some cases, but really they're all filling the tegmentum layer. You can see these nicely preserved in these Bell Canyon chitons, and it has a similar configuration to what you see in modern chitons, where you've got this vertical orientation of the canals at the dorsal surface. These feed into these horizontal canals that then course through the shell plate and exit both anteriorly as well as laterally. So you see a similar configuration to what you have in modern chitons. And here what you have is some epoxy filling of SE canals in modern chitin, just to give you a feel for what the canals themselves look like. So here, it's like you're inside the shell plate looking up at the dorsal surface. So you see those horizontal canals that are extending all the way to the anterior and lateral surface. At the very dorsal surface of the shell plate, something unusual happens in modern chitons where you get some enlargement of some of these regions called megalasthenes, and you get a branching of very fine canals called microasthenes. So this is seen in virtually all modern chitons, but you don't see it at all in the Permian chitons. So if you recall that whole valve that I showed you before, the whole valves, you didn't see any small canals, no large, relative to the large canals. It's all large canals, and thin sections show the same thing. So you have a very uniform size of these canals. So it's beginning to look a little bit modern in the late Paleozoic, but the SE canal system hadn't, in a sense, fully matured yet by this time. Another thing that these Bell Canyon chitons show us is really fine details of the articulamentum layer. And these are some of the earliest, in fact, roughly the earliest good examples of cuts or incisions in the projections of the articulamentum. Now, most modern groups of chitons have this. The Lepidopleurids, the primitive chitin group, does not have cuts in the insertion plates, but all other modern groups have. Now, in these Bell Canyon chitons, you can see these slits are very nicely preserved, but one strange thing about them is if you compare to the modern cuts right here, you tend to have just one or a couple cuts on the intermediate shell plates, whereas in these Bell Canyon forms, you see a lot of these different cuts here. And not only that, you see both cuts and grooves on the sutural laminae, as well as the insertion plates. You don't see that in modern chitons. The cuts are only on the insertion plates. So this doesn't seem to pass the any test of similarity. So these cuts were almost definitely convergently evolved compared to the incisions that you see in modern chitons. Those must have occurred at another time, another place. And a similar sort of conclusion had been reached with these really strange chitons multiplacophoras, where they've actually got slits long before other chitons. You're going back to the Silurians, so Silurian compared to chitons proper, the Permian. So these guys almost definitely independently evolved that as well. So it's not until the Mesozoic that you see typical cuts properly. And this is somewhat too bad, because these slits in the insertion plates, because of the fact that one major group of chitons lacks them, all other chitons possess them, it could have potentially provided a nice upper bound to the time of origin of the chitin crown group. But now, if these slits here, if they appear to be convergently evolved, it's difficult to infer these. And Jakob Winther has argued that the origin of the chitin crown group is from the late Paleozoic, based on both molecular evidence as well as the fossil record. And molecular evidence, perhaps with the fossil record, I would say that that's not terribly clear. Certainly these late Paleozoic chitons, the slits they have are different. So I would say you have to be a little bit cautious in that. Now, another thing that these Bell Canyon chitons show us is is that the chitons were really remarkably diverse in morphology in the late Paleozoic, especially compared to today. And it seems like the Permo-Triassic extinction really pruned the chiton tree. And these diagrams here are old, so they're in desperate need of updating, but the general pattern still applies. So you see here in the Permian a number of species. This green is from just the Bell Canyon Formation alone, so you can see what a significant deposit it was. Boom, big drop off there. And if you look at just some aspects of form, length to width ratio of intermediate and tail valves, you can see much more disparate in form prior to this. And I've done a multivariate morphometric analysis, but I'm a little bit embarrassed by how it looks because that also needs to be updated quite a bit. So, but just it passes the eye test. These late Paleozoic chitons are certainly very disparate in form compared to modern ones, more disparate than modern chitons. And this pattern was probably even stronger based on the fact that obviously there's a lot missing from the chiton record, which people have commented on before, like Stephanie Kropowski. So I tried to keep chitons alive in an aquarium. I didn't try very hard, so they died very quickly. And what happened shortly after, almost immediately, the valves disarticulate. So it doesn't take these guys long for the valves to come apart. These valves are relatively thin, they're aragonitic, they're going to get bashed against rocks and destroyed. And essentially the only hope you have in many cases is if you can get some sort of mineralization like silicification. And Leslie Turns has really demonstrated nicely how silicification has helped us get a really much better picture of chitin evolution through the Paleozoic. And this is certainly true for the Bell Canyon Formation. And just for fun, just to try to get a feel for, well, how much might be missing from typical Paleozoic deposits, I did a rarefaction analysis using the chitons from the Capitan Reef. And if you keep in mind here that typically most chitin deposits that are known, most localities with chitons preserved, tend to have just a few individuals, like certainly less than 50. You can see if these assemblages were anything close, if these ecosystems are anything close to the Capitan Reef ecosystem, you're really missing a lot of the total species that are present. So that pattern, if you just compare late Paleozoic to modern, that pattern is even stronger with higher disparity everywhere in the late Paleozoic compared to modern days. So to sum up, this particular deposit is the most diverse, numerous, and best preserved of all late Paleozoic chitin assemblages. These fossils show a high morphological disparity and diversity at the end of the Paleozoic. It also shows that by this time, the SE canals were certainly present, and they had a typical modern configuration, but without the elaboration that you see in all modern chitons. So not quite fully modern yet. Not surprising, these are old. Also, you see a reduction to tegmentum, as well as slitting in the insertion plates convergently evolved within the Polyplacophora. It's easy to understand why slits would independently evolve. That sticks the chitin valve better into the animal, so better protects it. And obviously, there's still a lot to discover about the history of chitins based on a relatively poor fossil record that hopefully can be improved. All right, thank you.